Thank you very much. Thank you additionally. I know it's Friday afternoon. It's the last talk. Really grateful that you made it. I hope it will be interesting for you. I'm Thomas. Most of you know me. I'm a principal software engineer. I have been with the company since 2013. Did various things. I was an engineer. I was head of software architecture. I was a team lead. And right now I'm a principal software engineer working with the Illuminati team in the revenue management domain. I'm going to talk about building evolutionary architectures. These ideas are not mine, so there needs to be credit where credit is due. There's this book called Building Evolutionary Architectures by Neil Ford and Rebecca Parsons and Patrick Kuhr. They're all involved with ThoughtWorks, like Rebecca Parsons is the CTO, Neil Ford is an enterprise architect there, and Patrick Kuhr is a team lead. So there is a question that I'm asking a lot of times when I'm doing talks about architecture, and the question is like, what is software architecture? The reason is, if you speak with architects around different organizations, different companies, if you ask them what is software architecture, the chance is pretty high that every single one of them gives you a different definition of that. So it's always a good thing to think about what software architecture is. And most of the time, you have these different non-functional quality attributes, you know, like security and data and auditability, the requirements themselves, performance, legality, the scalability. The list is endless. If you go to Wikipedia to look at the list of the non-functional quality attributes, you get a list of 300 terms. So all these illities you can have. But it's hard to define that up front. It's hard to define that in a big document. So even the Greek philosophers like Heraclitus, and you heard that sentence pretty much before, I'm pretty sure, the only thing that is constant is change. Everybody heard that. Everybody can relate to that, especially in software engineering, changing requirements, changing architectural decisions. So the question for an architecture is, or from an architectural standpoint, is if change is constant, how can you build an architecture that is not gradually degrading? Right? How can you keep it from degrading? How can you stop it from degrading over time? And how is long-term planning possible in this kind of environment? How can you plan for this constant change if you don't even know what that change is all about? So my personal definition, or at least the definition that I'm resonating most with, is that the architecture is the set of decisions that you want to get right early on in the project, right? The decisions that basically are hard to change later on. Mr. Ralph Johnson said that, and the question is, how can we build an architecture that expects change, that welcomes change, right? How can we build an architecture that can actually evolve over time, adapting to all these changing requirements, adapting to all these changing market conditions? And this is the question we're going to explore today with a few principles. So let's start with the definition of evolutionary architecture. So an evolutionary architecture supports incremental guided change as a first principle across multiple dimensions. And we will hear what these terms mean in the sense of evolutionary architecture, but this is the definition we're going to start with. So let's talk about incremental change. What does that mean? What does incremental change mean? And some of us are doing that already. So there's two aspects of incremental change, which is the first one, how are teams developing the software, and the second one is how do teams deploy it, right? So it's about the software delivery process, and it's about the putting it into the operations. And this is not something new. This is actually something that has revolutionized the industry for a few years already. Who here has read one of these two books? One. Two. Okay. I advise everyone to actually read them because everybody says they're doing continuous delivery, they're doing continuous integration, but when you ask some questions and when you hear the answers, you understand that, well, they're kind of doing it, but they're not doing it right. So if I ask your team, or if I ask you, can you release your application at any point in time? During the night, during the day, with a half-finished feature? If you say no, then you're not doing continuous integration and continuous delivery. You should be able to release your application at any point in time. If this answer is no in your team, then you should revisit your processes. So there are a few patterns. I won't go into detail with these continuous delivery practices. Read the books, read online. There's a lot of resources about that, the whole DevOps movement, everything built on that. But there's a few patterns that we can already apply in our organization. For example, canary releases, right? Releasing multiple versions at the same time and upgrading the services while they're running. Feature flags, for example, is another pattern that you could use to incrementally change it, right? We're deploying the application the whole time and we're just flipping the switch once we think the feature is ready. Or we flip the switch once the feature is ready for testing, right? We can emulate personas to activate these feature flags. So the public won't get the feature, but somebody who is a tester can get the feature enabled. Branch by abstraction, it's a pattern that's not very well known, but it's a pattern to do big refactorings in the code without having this long-living feature branches, right? If you have long-living feature branches, then you're not doing continuous integration because continuous integration means that every single commit goes into the main line. So if your feature branch is 1 week or 2 weeks for a big feature, then you should look at that pattern because that enables incremental development even with big features. And you should build anti-corruption layers. You should isolate yourself against, for example, external vendor libraries. You should isolate yourself against other dependencies because then you can react to change, right? So we have a new contract with a new vendor. If you don't build an anti-corruption layer in the middle, you will have a hard time changing all the code that is related to that vendor. Okay, so that was an incremental change, but more importantly is the guided change. So what does guided change mean? It means, okay, you don't want the architecture to degrade over time, but you don't just want it to evolve into any directions, right? So if we look into evolution, only those that can survive in the environment will adapt and will survive and will produce new generations. And the same is true for an evolutionary architecture, right? So we need to make sure that the evolution of the architecture is guided in a certain direction, in a direction that we want it to evolve. And there is an idea from evolutionary algorithms, also machine learning or neural networks, which are fitness functions. Who has heard the term fitness functions before? Okay, yeah, a few people. A fitness function is basically an objective function that tells something if it is fit for the job or it isn't, right? For an evolutionary algorithm, it would call that function on itself to validate that the function itself or the algorithm itself is still doing its job correctly, right? If this function fails, the evolutionary algorithm will normally destroy itself. Like a cell, right? If a cell in the body understands that it's not doing the job anymore, it normally dies. It puts the trigger and kills itself. So again, fitness function is a particular type of objective function that is used to summarize how close a given design solution is to achieve the set aims. So for an architectural fitness function, there's various sources, right? So it can be metrics, it can be tests, it can be logs, can be runtime analysis. It can be very few, a lot of things that is objectively measurable, and that's the important part. A lot of quality attributes in architecture are interpretations of certain people, right? The enterprise architects, how they're called nowadays. They interpret these quality attributes and they come up with numbers and, you know, they say this is how it's done or this is how it should be done. These request times are acceptable. This is not what we want. We want an objective measurement, right? We want to be able to validate our architecture with metrics, with measures that are not open for interpretation. So let's talk about the criteria a bit. There's different categories of these fitness functions. I will explain them one by one now. So one is the atomic fitness function. So what is an atomic fitness function? An atomic fitness function is validating a single context, right? Something that is on its own. It could be a single service. It could be a lambda function, for example. So everything that is a single context is an atomic fitness function. The opposite case is the holistic fitness function, where you have some kind of shared context, right? Integrated environments with other services, for example, the whole production environment, a staging environment, anything that is kind of shared and has different services, most of the time even across domain or team boundaries. And there's also differences in how those fitness functions are triggered. So there's the triggered fitness function, which is coming from a pipeline or a batch, or you run a command to actually execute it, right? So if it's a step in the pipeline, it's going to be a triggered one because it's only triggered by the step before, right? If the step before fails, it's not going to be triggered. Or you have a make file where you have a target where you just say make fitness function and it will execute it. And the other way is a continuously running one, right? Something that is continuously validating, that is continuously running a background process within your architecture that constantly measures, constantly puts metrics and evaluates its fitness continuously. So let me give you a few examples. So I put up a little matrix here. So the atomic and triggered ones, the most obvious are unit and functional tests, right? So in your single context, you have your unit test, you have your functional test, you make sure that the requirements are there. It's an atomic function that you run in your single context. Static analysis, right? Gathering static code metrics, analyzing the coupling, making sure that the modules within your service are sufficiently isolated. These are all atomic things. So let's go into the holistic and triggered. So consumer-driven contracts, right? So we have a shared context. There's a service A and service B, and they're integrating through some contract. So you need to validate that the contract of service A adheres to what service B expects. And consumer-driven contracts are a perfect way to do that. End-to-end tests, for example, another thing which is a holistic and triggered fitness function, or, for example, load and performance tests. So atomic continuous fitness functions, what could that be? Is there someone who has an idea? Correct. So monitoring and alerting, they're continuous fitness functions, right? So you say, I have an alert if this condition is true, then please call everyone on the team because we're down or whatever. Tracing, logging, another example of that, or service level agreements, service level objectives. These are all continuously evaluating the architecture. So what is a holistic and continuous fitness function? Chaos engineering principles, chaos monkey, conformity monkey, the Simian army, reboot roulette. I'm not sure if you heard it. It's something where you constantly reboot every single node in your cluster one after one, and it's continuing all the time to make sure that your platform is actually resilient, and also the applications that run on the platform are actually resilient. But again, also monitoring and alerting, right? So you can monitor across multiple contexts. You can monitor, hey, what is the trace, if you have a call trace between 3 services, what is the time to go from service A to service C? Okay, so we have talked about the fitness functions. How can we define a fitness function fit for a specific context, right? For you as a team, it might be the question like, what is important for us, right? You don't want to capture everything. I mean, defining those functions work, and we shouldn't invest into something that is not really useful to us. And you can do that with a simple spider graph, basically. So it's a really helpful tool. You put a bit of non-functional quality attributes around, and then you decide within the team, hey, what's important actually for this context? What's important for our service? Is it like the data security? Is it the auditability? Is it internationalization? And you just in the team, you dot vote, you say, okay, these are the things that are really important to us. And that helps you actually find out what kind of fitness function you should define. You only want to guard the important parts of your architecture. You don't want to guard everything. If you guard everything, you're not having innovation anymore, right? You want the teams to be able to innovate in different parts. You only want to guard or guide the most important dimensions of your architecture. So let me give you a brief example. This is a bit of Python code. Continuous atomic fitness function for performance. So it's just a while loop. Here you have a period of 5 minutes. Then you say, well, the high water mark for the 90th percentile in milliseconds is 50. You get the RPM for the period. And then you can actually do things like, okay, under scale, I allow my architecture to be a little bit less performant. Right? You don't say just one number and you compare it to one number. You say, if we have over 50,000 requests per minute, I allow it to go to 120 milliseconds. If I have over 100,000 requests per minute, I allow it to go to 160 milliseconds. Right? So you can define bands of values, because sometimes it's really hard to come up with one exact value. It has to be below 120 for all cases. That's just not practical enough. Right? So this would be a very simple example of such a fitness function. And as you see, because it's just a small Python script, it's very easy to integrate these automated fitness functions within your continuous delivery pipelines, right? Be it GitLab CI, or be it Jenkins, or be it whatever. It's really easy to execute this function as a continuously triggered or running background process within your continuous delivery pipelines. Right? Since it's functions and we can automate them, it's a way how the architecture can verify itself, right? You don't need this architect visiting you every quarter, having an architecture review with a team and asking like, why have you done it like that? Why have you done it like that? So your team can define, okay, this is important for us. We're going to automate that. We're going to integrate it in our pipeline. And this way, we're going to make our architecture self-validating. And that's super important. It's actually really good, right? Because you can innovate in multiple directions, but you have guarded the important dimension of your architecture in an automated way. So let's talk a bit about architectural dimensions. So everybody knows this architecture is the classic N-tier architecture, where you have the presentation layer, the business layer, persistence layer, database layer, right? Classic MVC. Who has worked with this kind of architecture before? Yeah, most of the people. I expected so. So here you have one dimension, architectural dimension, that you can evolve. The dimension here is the layer, right? So you can change each layer independently from the others, and that was the original intent behind this architecture. But you have 4 opportunities, right? So you have 4 different layers that you could change. But if we change the perspective a bit, So right now we take a domain perspective look, and let's say we have a customer feature here, and it always goes through all the layers, right? Suddenly, you have 0 dimensions again. You cannot evolve this architecture on multiple dimensions because you always have to change all the layers that are available to you. So here is a classic microservices architecture, and isolated service architecture, be it self-contained systems, be it microservices. If you have n services, you have n dimensions, right? So if you have a myriad of services, you have a lot of possibilities on how you can evolve the different services in isolation, right? For service A, there's a total different architectural constraints than on service B. And this is the dimensions we want to evolve differently, right? For one, security is really important. For the other, high throughput is really important. So let's talk about evolutionary a bit. So when we look at DNA in biology, DNA always contains information from the previous generations, right? There is no DNA that's just existing, except the first one. I'm not sure how science is actually explaining that, but normally mom, dad, and you get the information from the previous generations through that. So evolution is impossible without the history, and architecture decision records are a real help for that. This pattern, basically, you as a team, you create a markdown file within your Git repository, you put a title, a date, status, context, the decision itself, and the consequences. You put them to Git, and then you can send out some notification, or you put it automatically to the wiki. You make that decision transparent, right? So you create a history of your architecture. You create a history of your decisions. So what's your path to evolutionary architecture? So decide which architectural dimensions you want to protect within your context, right? We have seen the spider graph. You look at your service, you put that spider graph up, you have some conversations in the team, and you say, which of these are really important architectural dimensions? Which of these should be guarded against? Then you define and automate the fitness functions, right? Like the one I showed you before, you can do that on multiple levels. You can do that on an atomic level, or you say you do it on a shared context with consumer-driven contracts, for example, where you say, I want to make sure that my upstream dependency or my upstream service is adhering to what I expect, right? Because if we don't do that, then the resiliency might not be there, right? There might be a new version being deployed, and we just break. The third point is that you should rigorously apply continuous delivery practices. And this is the question I've told you before. Ask yourself in a team, can we deploy our application at any moment, at any point in time, even with half-finished features being integrated into the main line, right? Constantly ask yourself that question, because if you at some point want to arrive to answer yes, then you are able to constantly, incrementally change your application, change your architecture. As we've seen before, shift to a domain-centric architecture. We have done that before, but it's really important because it gives you multiple dimensions on which you can evolve your architecture. And then document these architecture decisions and make them transparent, right? Help the other teams to understand what's your context all about. So further topics that I haven't touched: evolutionary data, hypothesis-driven architecture. So if we have objective measures, we can actually run experiments on the architectural level, right? So if we have objective numbers, it's easy to do experimentation. Organizational part, how do we have alignment? And also the governance part, right? How do we make sure that teams are making these kind of decisions in a way that helps the architecture going forward? So thank you very much. I hope you enjoyed it. So I think we have some time for questions. Thank you.